Hey everyone, welcome to BCP Med. In this video, I want to take a look at how the sterics of a given molecule impact how that molecule's conjugate anion is stabilized by a solvent, and how that impacts the acidity of that molecule. In particular, we're going to focus on how hydrogen bonds are disrupted by steric effects and look at quite a few example molecules. Let's go ahead and get started. It's important to remember that acidity is strongly influenced by the stability of the conjugate anion. It's an equilibrium, and the more stable the right-hand side is, the products, the more the equilibrium will shift towards that direction. Solvents can help stabilize the charged species. In fact, water is particularly good at doing so because of its hydrogen bonding. So for example, if you have a Cl- anion in aqueous solution, the waters will surround that ion, and each of the hydrogens will attack a lone pair on that chloride anion and donate their positive character towards it, which helps stabilize the negative charge through these hydrogen bonds shown here. However, a problem arises when solvent molecules are blocked from accessing the anion. Consider the tert butoxide anion shown here. If we dissolve this in aqueous solution, some water molecules would love to go and attack that O- because those very positive hydrogens are looking for centers of large electron density. So they're going to want to go ahead and approach and form hydrogen bonds to that O-. However, if you notice, those dashed lines are crashing in to the methyl groups in the tert butoxide ion. This is problematic. In fact, the tert butoxide ion is going to block access for water molecules to get to that O-. And so as a result, this anion will not be stabilized as easily by water. It's not to say that it cannot be. It's still possible. Waters can approach from a different angle. However, it is going to be more difficult. It is going to be sterically hindered. And as a result, its protonated form is going to be less acidic. It doesn't want to form this charged species, which is not going to be as stable. To get a better idea for this, let's go ahead and look at the acidity of some different alcohols. In general, the smaller the alkyl chain that we're dealing with, the less disruption of hydrogen bonding that's going to occur. For example, let's consider methanol, ethanol, and propanol, 1, 2, and 3 carbon chain species. Their acidities, if we were to go ahead and look at the pKa's, are going to fall in this order, where methanol is going to be the most acidic, followed by ethanol, and then finally propanol. Why is that the case? Well, because the methanol disrupts hydrogen bonding the least. If we imagine we are a water molecule and we want to approach the conjugate anion of these alcohols, we want to get to that oxygen with as little in the way as possible. And the longer that chain gets, because especially it can rotate in space, because those are single bonds, that chain can really disrupt anything getting around that oxygen. In fact, once we get to things like pentane and hexane, they practically become insoluble in water completely, because that chain becomes so long it'll start wrapping around the sides of the molecule and completely destroy any chance at hydrogen bond stabilization. Another thing that we have to consider is the substitution on the carbons, how much stuff is around it, not just in a straight chain. The less substituted the carbon is, the less sterically hindered it will be, and the less disruption of the solvent effects. For example, let's consider these molecules here. We have a primary alcohol, a tertiary alcohol, and a secondary alcohol. So the substitution is going to go from left to right, primary, tertiary, secondary. So if we were to rank the acidities of these molecules, what would we expect? Well, these are all 4 carbon molecules, so we're not really worrying about the size of the chain per se, but the substitutions are going to matter. The acidities are going to go as follows. The most acidic is going to be the straight chain isomer, because here the straight chain is the most out of the way. It is the least crowded onto that OH. So once it deprotonates, the water can most easily access the conjugate anion to stabilize it. Second would be the secondary substrate. Here the water is going to have a little bit harder of a time, because once it ionizes, the whole backside is sort of blocked here by those alkyl groups. The front side is still available though. However, if we go ahead and look at the the tertiary carbon, it's going to be even harder for those water molecules to approach, because in 3 dimensions, this is a little bit hard to visualize since this is a 2D paper, but in 3D space, this is tetrahedral, and the overwhelming majority of the molecule is actually being hindered by those methyl groups. And so it's very difficult to approach the conjugate anion to stabilize it, and as a result, it will be the least acidic. Right? So steric effects play a big role in solvent stability in the liquid phase. However, something very different happens in gas phase, and a discussion of steric effects wouldn't be complete without mentioning this. In the gas phase, solvent effects are not at play. There is no stabilization from solvents, and so the steric effects that are disrupting solvent effects don't really matter anymore. Instead, something different, the polarizability, is going to largely dictate the anion stability, and as a result, dictate the acidity of molecules. So, for example, let's go ahead and consider the same 3 molecules that we just looked at, but now from the perspective of polarizability in gas phase. So if we look at the substitution, again, we have primary, tertiary, and secondary. And if we were to go ahead and rank their acidities, what we would find is that, in fact, the tertiary alcohol will now be the most acidic in gas phase, the secondary the second, and the primary alcohol will actually be the least acidic. Right? Why is this the case? Well, if we imagine that in the tertiary alcohol we were to go ahead and ionize this and put a negative charge there, the negative charge can more easily distribute towards all 3 of these methyl groups in the molecule, which spreads it out some and makes it more stable, right? Negative charges want to disperse. They don't want to be stuck in one place. They want to move around and minimize repulsions. So it's going to be more favorable in the larger molecule. In the case of the secondary anion, it can distribute to 2 carbons. In the case of the primary anion, it can only distribute to 1, and so it's going to be the least stable. So in gas phase and liquid phase, we see inverse trends related to substitution. Finally, I want to go ahead and look at a little bit more of a sophisticated example, which seems a little bit daunting from a superficial glance, but it's really not that complicated. We want to go ahead and rank the acidities of the 4 OH protons in this molecule. I totally made up this molecule. This is not a real molecule. But we want to go ahead and rank the OH protons, which are here, 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 and here. So this is going to be in liquid phase. Let's say we're trying to dissolve this in water or some other solvent. It's probably easiest to start with which one is going to be the worst, which is the least acidic. Well, do we have any tertiary hydroxyl groups? And the answer is yes. This hydroxyl group here is tertiary. It is going to be the least acidic because solvents are going to have the hardest time approaching it. All right, so this is going to be our least acidic. Number 4 is our tertiary alcohol. What is going to be next? Well, do we have any secondary alcohols? So we go and look and we find, indeed, we do have a secondary alcohol, this one here. So the secondary alcohol is going to be harder to stabilize by the solvent than the primary alcohol, and so as a result, the secondary alcohol will be number 3. It is the 3rd in ranking the acidity. Now, what about the remaining 2? Well, we see both of these are both primary, so these are both primary. So which one is going to be more acidic? Well, this one here has what is known as beta branching, which means that this is the alpha position and this is the beta position. At the beta position, we see that we have some alkyl groups attached there. And it turns out that although it's not directly next to the OH group, the beta position, crowding at the beta position, can have a steric impact. And so the one that has this beta branching is actually going to be disrupted a little bit and be a little bit less acidic than the one that has no beta branching. So the primary alcohol with no beta branching is the most acidic, then primary alcohols with beta branching, and then secondary and tertiary in that order. And with that, we've actually reached the end of the content for this video. Thank you guys so much for watching, and if you enjoy what you saw, please like and subscribe to the channel. If you want to learn more, check out our other videos in the chemistry playlists, and if you're looking to branch out, check out our other science playlists as well. See you next time!